They always like to include the current year in Maths Challenge questions, and so in this video we'll look at 10 Maths Challenge questions that I've written with the number 2025 in them. And 2025 is a really interesting number, so it's going to be a fun year for these problems. This could easily be a question in any of the 2025 maths challenges. Which of the following is equivalent to 2025 divided by 20 plus 25? Well, of course, 20 plus 25 is just 45, so we just need to work out 2025 divided by 45. You could do that as a long division if you wanted to. We can do 202 divided by 45 gives 4, because 45 times 4 is 180 with 22 left over, and then 45 times 5 is 225, so we get an answer of 45. You could make it slightly easier with a double-decker bus stop method. We could do 2025 divided by 9 first to get 225, and then divide it by 5 to get 45, because dividing by 9 and by 5 is the same as dividing by 45. But if we want to be really fast with these sorts of questions, there's one thing we should always prepare before we go into the maths challenge. Because maths challenge questions always contain the current year in some form, we should know the prime factorization before we go into any maths challenge of the current year. In 2025, we can factorize it as 45 times 45. It's a square number. There are going to be lots of interesting questions this year. And 45 is 5 times 9, so I've got 5 times 9 times 5 times 9, and the 9s become 3 times 3 each. So we've got that 2025 is 45 squared. We could also write that as 5 squared times 9 squared, and then we could write that also as 3 to the 4 times 5 squared. And knowing that and all those different forms is going to be useful in this year's challenges. And if we'd known that before we started question 1, we'd have been able to get the answer straight away. Here's a possible 2025 maths challenge question then. I have 4 children, all under the age of 10. If the product of their ages is 2025, what is the sum of their ages? Well, we know that the prime factorization of 2025 now is 3 to the 4 times 5 squared, or 9 squared times 5 squared. So I could certainly write 2025 as 9 times 9 times 5 times 5. Because all of the children are under age 10, there's actually no other way of doing this. If I made one of the numbers larger, the 5 would then have to be like 5 times 3, or the 9 would have to be 9 times 3 or 9 times 5 or something. We're always going to get 2-digit numbers. So this is the only way to do this with 4 different numbers under 10, and that must be the answer to this question. 9 plus 9 plus 5 plus 5 is 28 for C, and see how the prime factorization, knowing that in advance, makes that much easier. So let's go on to the next one. Can you solve this 2025 maths challenge question without doing too much work? How many factors does 2025 have? We can start with the prime factorization of 2025, which is 3 to the power of 4 times 5 squared. And you might start looking around for factors. And in fact, anything where we've got 3 to the power of something times 5 to the power of something, where the powers are less than 4 on the 3 and less than 2 on the 5, or equal to it, will be a factor of 2025, because I could multiply it by the remaining 3s and 5s to get up to 2025. So I could have, for example, 3 to the 1 times 5 squared is 75, 3 cubed times 5 to the 0, because anything to the power of 0 is 1, would just be 3 cubed, so that would be 27. I don't really want to just write all of these out one at a time though, so can we find a smarter way? Well, let's think about what we said there about 3 to the a times 5 to the b always being a factor of 2025, so long as a is less than or equal to 4 and b is less than or equal to 2. We could make a table then of the possible values of a and b. I can have a from 0 to 4 and b from 0 to 2, and if I took a equals 0 and b equals 0, that would be 3 to the 0 times 5 to the 0, that's 1, that's the first factor of 2025. I could do a as 0 and b as 1, that's 3 to the 0 times 5 to the 1, that would just give me 5 there. If I did 3 to the 0 times 5 squared, that gives me 25, and so on. Now, the idea is that you wouldn't really write all of these out. I'm just trying to explain how it works to you, because this gives us a really efficient method, right? I can match any of the possible values of A with any of the possible values of B, and there's going to be 3 options then for each possible value of A, and there are 5 possible values of A, so we know that the number of factors that there will be then will just be 5 times 3, which is 15, and we can work that out without actually having to write out the full list of factors. And so the answer there is D, 15. How many factors of 2025 are square numbers? Well, we start with the prime factorization of 2025, that's 3 to the 4 times 5 squared, and we now just think, what do we need to get a square number as a factor, right? A factor will be any combination here of powers of 3 and 5 where the powers are are less than the ones in 2025, like 3 to the 1 times 5 squared would be a factor of 2025. But to get a square number, let's think about what we need. So 36, for example, is a square number. It's not a factor of 2025, but it's equal to 6 squared. That's 2 times 3 squared, so that's 2 squared times 3 squared. I can also make square numbers like this, right? 3 to the 4 times 7 to the 8 times 11 to the 6 is 3 squared times 7 to the 4 times 11 cubed, all squared, because of the rules of indices and powers, right? I'll get 3 to the 2 times 2 times 7 to the 4 times 2 times 11 to the 3 times 2 when I multiply that out. So you can see that actually we only have square numbers when the powers are even numbers, because it means we can do something like this. We can halve the powers and get the square root of the number, and it would work exactly as so. So we're looking for values of a and b then, so that I take 3 to the a times 5 to the b. For it to be a square number now, our a and b have to be even numbers, and for it to be a factor of 2025, a has to be less than or equal to 4, and b has to be less than or equal to 2. So a really efficient way of solving this is to say, okay, I can have a is then either 0, 2, or 4, and b is 0 or 2. And I can match up those powers, so I can do 3 to the power of 0 times 5 to the power of 0, I can do 3 to the 0 times 5 to the 2, and so on. Because there are 3 choices for A and 2 choices for B, we get 3 times 2, or 6 options overall. The options for B equals 0 would be where we don't have any factors of 5. 5 to the 0 is 1, so I'd have either 3 to the 0, 2, or 4, giving us 1, 9, or 81. And for B equals 2, where 25 is a factor, we'd have either 25, 225, or the number 2025 itself, which is 45 squared, of course. But you don't actually need to write those down to solve the problem in an efficient way here. This is a classic maths challenge style question that could easily come up in one of the 2025 papers. What's the last digit of 2025 to the 2 plus 2025 to the 0 plus 2025 to the 2 plus 2025 to the 5? Let's first think about 2025 squared. If I multiply 2025 by 2025 and I did that multiplication, I would start with 5 times 5 is 25, and then there'd be a lot of other stuff on this first row of my long multiplication. On the next row I'd have to put a 0, and then there'd be some other stuff. On the next row there'd be 2 zeros, and then on the final row there'd be 3 zeros. But the point here is, regardless of what all of that other stuff is, the last digit here is just going to be 5 plus those 3 zeros, which is 5. The product of the last digit, in fact, is always equal to the last digit of a product. So when I'm looking at a multiplication like this, you can just do 5 times 5 is 25, take the last digit, and know that will be the last digit of the result. I cover that a lot in my online courses over at Mathsaurus, including the Go for Gold courses. So here, you see 2025 squared has last digit 5, and we've got the answer there for these two parts. We just now need to think about 2025 to the 5 and 2025 to the 0. So for 2025 to the 5, well, let's think about 2025 cubed first. By the same reasoning, if I do 2025 squared and then multiply it by 2025 again, well, we've just worked out that 2025 squared ends in a 5, and so does 2025. So by that product of the last digits is the last digit of the product property, this is also going to end in a 5. And in fact, by the same logic, any power of 2025, including 2025 to the 4 and 2025 to the 5, they will all end in 5. So actually the last digit of this one is also 5. So we've just got 2025 to the 0 to think about, but x to the 0 is always equal to 1, except when x is equal to 0, of course, when it's undefined. So 2025 to the 0 is equal to 1, and then the last digit of this sum will be the sum of the last digits. If you imagine adding those all together, I'm going to get the same last digit as if I just add 5 plus 1 plus 5 plus 5, which gives me 16. The last digit of that is 6, and so the answer here is E6. Here's another question that could easily be a 2025 maths challenge question then. Radhika writes down the digits 2, 0, 2 and 5 in some order to form a 4-digit number. How many numbers that can be formed in this way are divisible by 15? So for a number to be divisible by 15, it just has to be a multiple of 3 and a multiple of 5. Again, you can check out the other Mathsaurus videos and my online courses if you want to know more about all of these rules. But I'm going to assume that you're happy that this would be equivalent to finding numbers that are multiples of 3 and multiples of 5. Now, what sort of numbers are we looking at here then? 2052, 5022, 2205, anything that's a permutation of 2025, obviously not including things that start with 0, because they wouldn't be 4-digit numbers. So the digit sum test for divisibility by 3 and by 9 says that if I add the digits together, so here I get 2 plus 0 plus 2 plus 5, that gives me 9. That means that any number with those digits because its digit sum is 9, that will be a multiple of 3 and actually also 9 here, right? If the digit sum is a multiple of 3, the number's a multiple of 3. If it's a multiple of 9, it's a multiple of 9. Really core maths challenge content for the divisibility tests. So as we said, because 15 is 3 times 5, they don't have any factors in common. That means that to look for multiples of 15, we're just looking for multiples of 3 and of 5. So which ones are then multiples of 5 is all we need to know then, because we know they're all automatically going to be multiples of 3. So to be a multiple of 5, the number just has to end in a 0 or a 5. So we've got two cases to consider. If we are ending in a 0, we could have 2250, 2520, or 5220. Essentially, I've just got 3 choices as to where to put the 5, and the other slots are going to be filled up with the 2s. If it ends in a 5, I can do 2205, I can do 2025, but 0225 I can't do, because that one would not be a 4-digit number because it starts in a 0. So the total number of options here that are multiples of 15 is 3 plus 2, which is 5, and the answer here is C. This is a tough question. I'll be impressed if you can get this one right. Bob has forgotten the code on his 4-digit padlock, but remembers that the code does not contain 0, that the first digit is not larger than the second digit, and that the third digit is not larger than the fourth digit. How many possibilities are there for his code? Well, let's have 4 spaces for the digits and just think about the sorts of codes we can have. Something like 3755 would be valid here. There are no zeros, the first digit is not larger than the second, and the third digit is not larger than the fourth digit. Nothing says they can't be equal. So the first digit is basically less than or equal to the second one, and the third digit is less than or equal to the fourth one. And we've got effectively then 2 independent problems to find these 2-digit numbers for the first 2 digits and for the second 2 digits, right? So I could think about looking for a 2-digit number with digits A and B, where A is less than or equal to B, and of course we're not allowed to use 0. Now, I'm going to list them all out here. I don't think you actually should list them all out. I think if I was doing this, I would hope that you would spot the pattern here and be able to work this out without writing them all out. But you can see that there are 9 numbers like this that start with a 1, 8 that start with a 2, 7 that start with a 3, 6 that start with a 4, and so on. So that the total number of options here is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. That's the 9th triangle number, and so there's a formula that we can use here. We're just adding the numbers from 1 to n together. You do n times n plus 1 over 2. So here we can just do 9 times 10 over 2. I've got more content about this in my online courses and other videos if you're interested. Of course, you can also just add the numbers 1 to 9 here together. It doesn't take too long. But that fact really comes up a lot in maths challenges and is very useful when you've got larger numbers involved as well. 9 times 10 divided by 2 is 45. So there are 45 ways of choosing that 2-digit number then to begin with. But if there are 45 ways to choose that first 2-digit number, it's exactly the same rules for the second 2-digit number that forms the third and the fourth digits, so there'd also be 45 choices for those, and no reason why we can't repeat them, and nothing in the question says that we can't do that. So overall, there are going to be 45 times 45 choices, and of course 45 squared is equal to 2025, something you should really know if you're going into a 2025 maths challenge question. And so the answer here is D, 2025. Here's a 2025 maths challenge question that's got a neat trick in it. Which of the following is equal to 2025? We've got 5 options here, and clearly we're going to need to use the options to answer this question and to consider them one by one. But rather than actually working them all out, I'm going to just think about the last digits. We know the last digit of a product is the product of the last digits. So I can know that 23 squared has the same last digit as 3 times 3, so it's 9. 41 squared has the same last digit as 1 times 1, which is 1. And so when I add those together, the number I'm going to end up with has last digit 0, because 9 plus 1 is 10, and 0 is the last digit of 10. So if we go through all the different options, we can see whether we've got any candidates that could be 2025. So A would end in a 0, that's not going to be 2025. For B, we'd have 4 squared is 16 and 9 squared is 81. The last digit of that is 6 plus 1, which is 7. For C, it's 5 squared and 8 squared, so that's 25 and 64. And the last digit here would be 5 plus 4, which is 9. For D, we've got 7 squared plus 6 squared, so 49 plus 36, and the last digit for this one is 9 plus 6, which is 5, so that's more promising because 2025 does end in a 5, so that's the first one that could be the answer. We don't know it is yet because we haven't checked the last option, as we might need to do some further work if E also had last digit 5. But E actually doesn't have last digit 5, it's 64 plus 25, so that would end in a 9, and the only option that can work here is D, so that would be the answer. There's another sneaky route to the answer here as well, which you might also spot a Pythagorean triple. So if you've studied Pythagoras' theorem, you'll know there are some Pythagorean triples that satisfy it in right-angled triangles, where we've got 3 squared plus 4 squared equals 5 squared in this right-angled triangle. But you can scale these triples up by any amount and you still get Pythagorean triples. So if I multiply the numbers by 9 here to get 3 times 9, 4 times 9 and 5 times 9, that would be 27, 36 and 45. And so that's another Pythagorean triple that says 27 squared plus 36 squared is 45 squared. And going into a maths challenge in 2025, we would want to know that 45 squared is 2025. And so we might just be able to spot that quickly if we are really on the ball. 2025 students sit equally spaced around a circle. Each student is only friends with the 4 students closest to them, the 2 on their right and the 2 on their left. How many pairs of friends are there in total in this circle? Well, let's think about what this would look like. I'm not going to draw out the whole circle, of course, but let's imagine we're just looking at a part of the circle and we've got a few of the people represented as dots here. So we're saying that this person here, for example, would be friends with all of these people. So I could form a line here where there is a link of friendship. If I then do the person next to them, they're also friends with the 2 either side of them. I could do this one here, they're friends with the 2 either side of them, and I could keep building up this picture until I'm sort of reasonably satisfied I know what's going on. Because if I go through all 2025 people and do this, in total I'm going to have drawn 2025 times 4 lines, because I'm adding 4 friendships for each person that I consider. But when I look at the friendships, all of them have been counted twice, because if person A is friends with person B, then I will have counted that friendship when I looked at person A and also when I looked at person B. So if I take this approach, I'm going to have drawn exactly double the number of lines that I need to represent the friendships, so I need to divide that by 2. Now, don't multiply 2025 by 4 and divide it by 2, just recognise that 4 divided by 2 is 2, so I can just do 2025 times 2 and get the final answer here, which is 4050, and the answer here is C. This is an incredibly hard maths challenge question with 2025 in it. Raphael writes all of the positive integers whose digits are only 2s or 3s in increasing order. So his list starts 2, 3, 22, 23, 32, 33, 222, and so on. How many digits will the 2025th number he writes have? We've got to look quite far into the sequence then, and so let's just start playing around with this and thinking about how many numbers there are with each different possible number of digits. So there are 2 one-digit numbers to begin with, the 2 and the 3. There are 4 two-digit numbers we can see here. And then how many 3-digit numbers are there? Well, we've got to put either a 2 or a 3 in each of these boxes. So there's 2 choices for the first one, then 2 choices for the second, and 2 choices for the third. That would give us 8 possible 3-digit numbers with just 2s and 3s in them. If I add a 4th digit, then I've got another 2 choices there, so that would be 16 choices for 4-digit numbers. So we've got 2 to the 1, 1-digit numbers, 2 squared, 2-digit numbers, 2 cubed, 3-digit numbers, 2 to the 4, 4-digit numbers, and so on. So let's see where 2025 is going to end up in this, right? We've got 1, 2, 3, 4, and 5-digit numbers, and there are this many of them, 2, 4, 8, 16, and 32. We'll just start there. And if I then look at the total of these numbers, like the cumulative total, I mean, then I will know how many numbers there are with fewer than 4 digits, fewer than 5 digits, and so on, right? So if I do 2 plus 4 is 6, then add 8 to get 14, add 16 to get 30, add 32 to get 62. So this means we've got 62 numbers here which have 5 or fewer digits in them. So the 62nd number in the list will be the last 5-digit number. So we need to keep going a bit further, and there will be 64 6-digit numbers. That will take us to the 126th number. There are 128 7-digit numbers that take us to the 254th number. There are 256 8-digit numbers to take us to the 510th number. 512 9-digit numbers to take us to the 1022th number, and then there will be 1024 10-digit numbers to take us to the 2046th number. So the 2025th number is going to be somewhere in this set. It's going to be one of those numbers that has 10 digits, and the answer to this question is B, 10. So very well done if you got that right. Well done if you've made it this far. Don't forget there are free courses for the first, the primary, the junior, the intermediate and the senior maths challenges and the follow-on rounds that you can take over at the Mathsaurus website. Or if you want to practice more questions like this with 2024 in them, they could still be very relevant for this year. Have a look at the video on the screen now.